This is section 7.6, tessellations. Okay, so the first thing there is tessellation is a covering of a plane with non-overlapping congruent regions. Okay, a lot of times when I think about this, I think about like bathroom tiles or kitchen tiles. So basically you've got a bunch of, square or rectangle, or they could be hexagons, or a lot of different shapes, but a bunch of tiles that all kind of mesh together where there's no gaps in between them, and they cover a big flat surface. That's basically what a tessellation is. Another example would be like bricks. So like if I had, say I've got something that's like a brick wall here, where you've got, your different bricks kind of going there like that, but they're filling that entire space and there's no gaps in between the bricks, even though you do have like the mortar, or with tiles you've got the grout and stuff. Basically you could put them all next to each other and it fills the entire area. Another thing would be like carpet tiles. Sometimes you get carpet that's in tiles. That would also be a situation like this. Honeycombs are another. So honeycombs would be more like, let's see if I can draw it here, more like hexagons matching together. But that would also be an example of a tessellation, because they would all kind of, it's not really right there, but you get the gist. They would all kind of form together with no gaps in between. Okay, and then a fundamental region is basically a region that is used to tessellate the plane. So it's basically just like if we had a tiled floor and the whole floor was our tessellation, one of the tiles would be a fundamental region. Or like if I look at my brick wall here, one of these bricks by itself is a fundamental region. Or like in the honeycomb example here, one of those honeycombs is a fundamental region. So I'd basically take this honeycomb and keep translating it a whole bunch of times around there, and it would fill up my whole, space or whatever. That would be a tessellation, and each of those little pieces there is called a fundamental region. Okay, so let's actually do some tessellations here. So you'll almost need to print out this sheet here. It's kind of hard to do it without printing out the sheet. You don't necessarily have to, but it makes it a lot easier if you do have this printed out. And what we're going to do is we are basically going to cut some different things out. So this first one, you don't necessarily need the sheet because you're just going to cut out a triangle. So this is going to be activity 1. It's in the book if you want to look at it. Otherwise, we'll just kind of walk through it together. But basically our goal here is to show that any triangle can tessellate the plane. So any triangle that you cut out of a piece of paper, we can move it around so it matches up and fills a whole paper. Okay, so what you're going to need to do first is cut yourself out a triangle. So I've got my little example here. And then, and it can be any size, any shape. They say scalene, so it's ideal if all your sides and all of your angles are different, but it's not going to be the worst case scenario if you don't have that, but it does make it a little bit easier to kind of follow along here. So then after that, you're supposed to label your corners. So I got A, B, C, and then mark the midpoint of each side. So what you want to do there, and it's kind of hard because you just cut it out randomly, but kind of line up your ruler against those sides, and like this one here, this side from C to B is about 7.5. So if I take that and divide it by 2, that would be 3.75, which is somewhere kind of in the middle of there. Try your best to find the midpoint of each one of those sides and mark those in. So like this side here from A to B is about 5, so 2.5 is my midpoint. And then from my A to my C, looks like about 4.5, so that would be 22.5 millimeters for my side there. So find your midpoints, get those marked in. And then after you get your midpoints marked in, what we're going to do is we are going to trace this triangle. So just hold your triangle down on your paper, and it can be anywhere, and trace it. And it's easier to do if you've got like cardstock or an index card or something like that, but my stuff here is just paper because that's all I can print on, so oops. Heck, what time am I doing this? Okay, so get yourself your triangle and then mark in your different little sides here. Okay, and I should mark my midpoints here too when I do this. So my midpoint here was that side, here is there, and then right there. Okay, so then what it wants us to do is it wants us to take our triangle here and rotate it 180 degrees about a midpoint. So I'm going to pick this bottom side's midpoint here, so C to B, and I'm going to take, and when I rotate 180 degrees, it's basically flipping it completely around. So basically I'm just going to take it, and I'm going to turn around that midpoint there. So now my midpoint should still kind of match up with each other, and then your ends of your triangle should match up as well. So if you didn't get it marked quite exactly in the middle, you can also just line up the ends of your triangles kind of like that, and then trace around that one. And I'm going to mark my midpoints in again, and here this would be my A, B, and C in that case. So basically I just took it from here originally, turned it a complete 180, and now I'm to there. Now I could also do that with any of my sides. So say maybe I wanted to make one over here. What I could do is I could take and I could spin off of my side AC here, spin my 180 like this, match my midpoints up kind of again there, and you can also match your corners up, and then trace that there. And you can do this a whole bunch of times. Usually like 4 or 5 times is good enough for like an assignment or a quiz or something like that. I'll just kind of keep turning around here. So this was my side A, B, C, and then my midpoints there, there, there. I'm going to turn back up this way. So if I do that, I can do the same thing here. And you'll kind of see as you keep going around, so I'll do some more off to this way here. So this was like this, so if I take, kind of go back up this way, it'll somewhat start following kind of a pattern here where everything will fill in on itself. So you could basically fill this entire page up if you wanted to with these triangles being repeated. So I could keep going this way, I could go back this way if I wanted to. Oops. And then what should happen here is if I did want to, so I kind of got a little gap in here, if I did want to flip back to this, if I rotate back around there, it should fit right into that gap there. So it should, if you did this on the whole sheet, it should fill all your gaps. Now you might have some issues like mine doesn't exactly, points don't exactly match up there, but pretty close for, you know, just tracing this by hand. Okay, so that's our first look at a tessellation. So what we can get out of that is any triangle, because we all cut out different ones, can tessellate the plane. So any triangle, scalene, right triangle, isosceles, those would all fill up this entire space and there would be no gaps. Okay, let's try another one here. So this one is every quadrilateral can also tessellate the plane. So, or quadrilateral region, I guess. So here the example they want us to use is back on this sheet here. So it's this one for activity 2. It kind of looks like a weird boomerang type thing. So I've got that one cut out. And then what you want to do with ones that are 360 like this, you want to label all your corners again here. So before we did ABC, I'm just going to label these 1, 2, and 3, or 1, 2, 3, and 4. So I got 1 here, 2, 3 is kind of like this corner that goes in a little bit, kind of dented in, and then 4 is that real small one there. So we're going to do the same thing after we get this cut out here. We are going to trace it. Hold it down the best you can and trace around it. This one's always hard with that little tail thing sticking out. Okay, and then once you get it traced, again, we want to label those little numbers in there. So 1, 2, 3, and 4. And how this one works is basically you can do a whole lot of things with this. You could do where we kind of rotate off of one of the sides again. So like say we want to take And, well, it does say that, I guess, rotate about the midpoint of one of the sides 180 degrees. So say I want to go off of my side here, 3, 2. If I take, and you can mark your midpoints in if you want to, but I'm not going to. I can take and rotate around like this, and then just kind of swap. So basically my 3 and 2 kind of swapped places with each other. So now I'm going to line it up like this. And that side should be the same length going from 2 to 3 as it is from 3 to 2. So everything should match up okay. So then trace that one in. Just do your best. I know it's hard with these little tails. Okay, and then I'm also going to label this. So that was 2, that's 3, little one is 4, and then that one's 1. Now I'm going to rotate again off a side. So basically, if I rotate off my side 1, 2 here, I'm going to rotate like that. Okay, so before I had like this, I'm going to rotate it around, so basically my 1 and 2 are kind of swapping locations. So like that. Oops. Little tail is so hard to draw. Okay, and then again, put my little labels in there. So 1, 2, 3, and 4. Okay, so what's kind of neat about these now, I don't know if you think it's neat or not, but it's kind of neat to math people. What's going to happen here is, if you think about it, what we've learned before is that all the corners of a quadrilateral, no matter, you know, what it looks like, if it looks like something weird like this, or a square or a rectangle or whatever, all of our corners always add up to 360. And what's kind of neat about this is 360 is also all the way around a circle, right? So basically here, if I think of this 1, 2, 3, and this missing spot here being all the way around kind of this center point here, all 4 of those points that go in there, this one, this one, and this one, or sorry, this one, this one, this one, and this little missing one here, all have to add up to 360. So what should happen here is this little gap, if I rotate around here, my side 1 to 4, and kind of slide that in there, that little missing part there should fit perfectly with the little part of our boomerang there that kind of sticks out for angle 4. So let me draw that one in and kind of show you. Okay, so it kind of comes around like that. Again, my drawing's not great here, but you got 4, that one's 3, 2, and 1. So what happens here is, because this all the way around here has got to add up to 360, I can take 1, 2, 3, and 4, since those are all the corners of my little shape that I started with here, and put those around in a point like that, and it'll have to add up to 360 and match up perfectly, because all quadrilaterals add to 360. So like if I, say, wanted to fill this little gap down here, I've got a 2 and a 3, so I'm missing in my little gap a 4 and a 1. So if I went back here and went and took and turned my shape around this way, like that, and kind of did my tracing here quick, this would be 2, 1, 3, and 4. So you can see there how that little gap is kind of the same one we were missing up here. So if I were to rotate around like this, that 4 would fill in that last little spot there. And then again, around this circle here, I've got 1, 2, 3, and 4. Okay, so that works with any quadrilateral, whether it's a square, rhombus, kite, whatever it is, you can rotate it around like this and it will tessellate the plane. Okay, so every single quadrilateral, whether it's convex or non-convex, because you can see this one here is non-convex, that still works for this, and I could fill this entire sheet up with little boomerang type things. Okay, next thing here, we're going to jump to our example sheet. So that looks like this. And basically, we're not worrying about that. Basically what they have here is just 2 examples they want us to do. So the question is, will a regular octagon tessellate the plane? Okay, so basically they want to know if we had an octagon, so a little cutout like this, but it had 8 different sides and 8 angles that all matched up because it's regular, if we could fill the entire page with octagons and not have any gaps in between. So what we can do to figure this out is we can actually use some formulas that we've used before. So what we can do is we can use, you remember that formula where it was the n minus 2 times 180? And then that gave us all of our different angles. So like if this was our shape here, that would give us all of our inside angles added together. And then to find what one of them was, we took that value and divided it by n, which would be our number of sides. So like here for our regular octagon one, I'm just going to do it down here. You can follow along in these little blanks if you want to, but you don't have to. I'll just kind of talk you through. So if I use that formula for a regular octagon, octagons have 8 sides. Heptagon for the next one has 7. So octagons, if I do it here, 8 minus 2 times 180, 8 minus 2 would be 6, times 180 would be, it would be 600 plus 480, which would be 1080. And then I'm going to have to use my calculator to divide that. So then this is all of our angles added together for an octagon, and then we divide that by 8 to figure out what one of the angles is. So if I do that, 1080 divided by 8 gives me 135. So what it's saying there is if I had a regular octagon, I can draw this good enough here, something like that, that each one of those angles is 135, which is stuff we've done before. Now the difference here is we have to figure out if this is going to tessellate the plane. So if I drew a bunch of these octagons, could I fill an entire space up on this paper with no gaps? Well, how I do that is I take 360, kind of like I had on that last one with that quadrilateral, divide it by 135. If it comes out nicely, this would be yes. If it doesn't come out nicely to be like a whole number, then it would be no. So if I do this here on my calculator, 360 divided by 135, you get 2.6 repeating, which is not a nice number. So since that doesn't work, this will not tessellate the plane. So this would be no. Okay, and then for the regular heptagon, we could do the same thing. So B here, heptagon is 7 sides, so we do 7 minus 2 times 180, so that would be 5 times 180, which would be 500 plus 400, which is 900. And then we want to divide by 7 this time for a heptagon, which again, I can't do that in my head, so 900 divided by 7 is a crazy number here. So since it's a crazy number, 128.57-ish, squiggly equal sign means approximately equal to, this is probably more than likely not going to work. So if I did 360 divided by that crazy number there, probably not going to come out right. So if I did this here, 360 divided by second answer will get me what it says up there. It comes out to be 2.8. So again, they're a little bit nicer than this number here, but since it doesn't come out to be exactly a whole number, this would be no. Okay, now why this works for like quadrilaterals, so if I go back to my quadrilateral here, it will work for this. So this isn't one of them, but I'll just kind of add it in. If we had a 4-sided figure, that would be 4 minus 2 times 180, so that would be 2 times 180, which would be 360. And then I've got 4 sides, so if I did 360 divided by 4, I get 90, right? So basically that would be like a square would be a regular quadrilateral. So then if I took and did this last part here, 360 divided by 90, I get 4. So basically it's just saying you've got 4 little pieces there that would have to go together to make that 360. So if it was a 4-sided regular figure here, the answer would be yes. Okay, so I just gave you that example there because these ones both came out to be no. So I wanted you to see an example that actually would work. So all quadrilaterals like we had on the last page will come out nicely. No matter if it's a square or something goofy like this, it always will come out nice. Okay, back to our tessellations here. So with this next one, back on your activity sheet, there should be a hexagon here. You'll want to cut that out, and then you'll also want a piece of tape, because basically what you're going to do is you're going to cut out your hexagon, and then you're gonna take whatever you want to cut out and do like a little extra cutout here. So basically I just took my hexagon and cut like a little triangle out, and then you want to slide that to the opposite side. So I kind of took that triangle out there and slid it to this opposite side here. And then we want to see if a non-polygonal figure, or like a kind of like a goofy figure, will tessellate or not. So we're going to try this out here. So get yourself a cutout, and then whatever piece you cut out, take and slide that to the other side, and then I just used a piece of tape to hold that on there. Okay, so we want to see if we can fill the space with this little, kind of looks like a little tadpole. Okay, so I'm going to trace this guy. Trace. Okay, so something like that. Now with this isn't going to be one where we can take and turn here. So before we were taking and doing some turns and getting them to match up. If I take and turn here along one of the sides, I don't know that it's really going to match up. So what I can do instead is, since I kind of took this part and slid it over here, what I could think is, well, if I take this and slide it over, that opening there that I cut out should be exactly the same as this opening here that I moved over to that side. So I could kind of slide it over like that and trace that little one. Oops, not very good at this. Something like that. I could also take and slide it down here because the tops of these should match up. So I could also kind of take and slide it down like that. And it should, if I was better at tracing this, it would match up better, but you get the gist. So instead of rotating like we were doing on the last one, this is more like a translation when we're doing these. But still tessellation, because we can still fill this entire space here with this shape and have no gaps. So I could keep sliding that around there and try to fill that up. Okay, what else do I have here? Oh, so last thing here, tessellations can be spherical. So if you look in the book on page 416, there's just a picture of kind of a globe there, where basically you've got a bunch of little wedges that are kind of curve shaped, but still would fill that entire globe. So you can have this in like three-dimensional curve type things as well. Okay, so that's your book page there, 416, 1 to 10 all, and then 12. There are a couple questions on this sheet as well where you'll want to cut those out so you can kind of do your tessellating with those versus trying to draw them out by hand. It's a lot easier if you've got these to trace.